So in this video, I'll be talking about how to get the maximum angular frequency of a cylindrical cup with a radius of h and a height of r, and no water can spill out of this cup. So first, let's make a visual of what we're going to do. I got my pen. So here is the fluid. This the top there. And after it gets rotated, so you get some angular frequency, it's going to look like that. So let me erase that, my frequency. Okay. So first we'll start out with the basic equation of statics, dP dr. But in this case, we're going to have rho angular frequency r. We have angular frequency squared r here because of centripetal force. So this would be actually acceleration here, but the acceleration is angular frequency squared times r, which is the radius from a certain point. So that there is r. A certain height of h right there. So then we're gonna solve this equation. So it's some certain pressure from 0 to p. It's not super important. And then so we continue to solve this. Eventually, we're gonna replace that variable. And this variable right here is just a dummy variable. We could have used a different thing, but it just makes more sense. So, r squared. And pressure is equal to rho gh. So cancel. And we get the height is equal to squared, not squared. So we have found this height here from a certain point up. So now that we got that, we want to find the height at big R. So this is from the radius to the wall. Actually, no. Let's do height R equals big R into r squared over 2g. That there is the radius at the wall. So we solved for the certain height from the floor. We want the total height there. And we know that no water here will leave the system. Because if it did, that would be a lot more difficult to solve. So we need to find a distance from the lowest point in the container. Now let me draw a new picture down here instead of reusing that. So let's So we got the R here. Let's make this distance D. So that is the volume. So let's continue to draw this. And you got this. Now here now is H of R. It's H. Since no volume leaves, this volume here must be the same as this volume here. So volume original is equal to volume final. We're not talking about this here because that is the same. This moves up an additional height, which is what it's going to get to the maximum without spilling over. So as we continue to do this here, so the volume here, it's a circle, so pi r, not r, pi big R squared now, which is what we want to solve, times this height, this differential distance, d, which is what we're going to call the variable, could name it anything, is equal to this volume there. Volume. I'm going to try to shade it in as best as I can. There. So now our goal here is going to have to solve this volume. But in total, what we're actually trying to find is a big H, the height at which the water can go maximum without spilling, maximum without spilling. We know what big H is equal to. It's going to be R minus D. Pick any height here. This is going to be D. And this here is not. This is going to be R minus D. So we need to relate the R there to this side, this picture or this cup to this when it's spilling over. Plus the additional height is going to move up the cup, which it doesn't here. But to solve this, we're going to need the volume here to solve for D, since we already have HR. So let's get down to a more new page. So as you think of it, we'll have U again. But we're going to need to use an integral here to solve it. So this is some differential radius, as it's going to change as you go farther away from this point here. So R. As you look at it from the top view of it's a cup, circular cup, cylindrical cup, so it's going to look like a circle. We have some R here. We have some, this little shaded part here is going to be the differential volume that is changing. This differential volume here that's changing. So is going to be equal to this differential radius that is changing. Also times the circumference of the circle, since the radius is changing as you get farther out, the circumference is also going to get bigger. So we get pi r squared dr h, where we already know the height and that certain radial position. So, and I forgot a 2 here. It's on the circumference, so it's times 2 pi r. So now we're just going to do some algebra here as to solving this. So differential So the volume isn't changing, so we're just going to say it's a volume of V. And let's see. So now we want the radius of big R. So from 0 to big R is what we're trying to find. So now we can actually do that. We get pi squared 2 drh. And get the dB there. So you do that. You can take the pi. Oh, you don't take the R squared out. That is my bad. And I forgot the H here. What's that? That is the H. Ooh, that's bad. Okay. H, as we go up here. Is that what we got here? H of R equals big R. H R, little r equals big R is equal to angular velocity squared R squared over 2G. We can substitute that in here. So keep integrating. So we do that. And then the next thing, we're going to finally get the volume of this shaded area. So we're going to get the volume of the shaded area here, which is what we need. So this volume, that shaded area will equal to 4G. And now we can solve for the distance here. So the distance of the depression dip here, in which we have that equation of pi r big R squared d is equal to that. We now have the volume of the additional height air volume. So you can do is equal to pi, and this cancels out to a 2. And I believe that is all that cancels out. Actually, I think I messed up. I forgot that a pi here. I did not bring it. I have it there, but I did not bring it over here. So this pi cancel out that, and eventually finally get the dip now, which is the variable we need to find. Big height is equal to angular velocity squared to the 4 or G. Now this is a relatively simple problem to solve, since H is equal to R minus D plus H of R. And we have every single one of these variables. And it looks like I'm running out of time on my 15-minute video, so I'll see you in the end of the next video, where it's probably only going to be a minute long. So, see you.